Hi. So now I want to talk to you about arclength functions and arclength parameterizations. So first we're going to recall, right, the arc length of a curve. So we're going to use S for our arc length now. So S is defined to be the integral from A to B of the derivative of our vector function R, right, our position vector function R, right, as t moves between t equals A and t equals B. So remember, R traces out a curve C right here. And if we wanted to say from t equals A here to down here, t equals B, if we wanted to know the length of this curve, the way we do that is by taking the derivative of R, and then we integrate that the length of that derivative from A to B. Okay, so now let's say we don't want to know it just right between those two specific points, but we want to have a general function that will tell us the arc length at any given time t, sometime after A. Okay. Well, the way we do that is we're going to reparametrize R in terms of U, take that derivative, integrate from A to t. So this is a little fundamental theorem of calculus coming back in vector form. Okay. So the way we're going to do it is we're just going to reparameterize R using the U instead. We're going to find that length of R prime, right? So find that speed in terms of U. And then we're going to evaluate our integral from A to T. Now, sometimes they're going to give you a value of A to start at. If they don't, we're going to typically take A to be 0, as long as 0 is in the domain. If it's not, then, right, I usually just take the smallest number in the domain. Okay. So let's go ahead and practice a couple. So we are going to find S of t, so find that arc length function. Right, in terms of t, if this is our given r. So r is defined to be t squared, 2t squared, and 3t. Okay. So we're going to rewrite r in terms of u. So r of u, it's just u squared, 2u squared, and u cubed. Let's go ahead and find the length, right, of r prime. Okay, so first we'll find r prime of u. So 2u, 4u, and 3u squared. So far, so good. Okay. Now, how do we find the length of that? Right, square them, add them, root them. So the length. So, and by the way, so this is the length of this r prime. Let's take just one quick step back and think about what we're finding here. So r is our position, right? Still a position even if I just change to be u's. Okay. R prime then, right? This is the velocity vector. So what we're finding here is the speed. Right? So it's kind of like the positive version. So I don't care about the direction. I just want the magnitude that we're moving. Think about it. You're checking your speedometer as you go along. Okay. So square them, add them, root them. So 4u squared plus 16u squared, check my arithmetic, and then plus 9u to the 4th. Okay, you can go ahead and tidy that. So 20u squared plus 9u to the 4th. Oh, I'm going to keep tidying because I know what I'm getting set up for in just a second. Notice that they each have a u squared you could factor out. So this is my last tidying step, and then I'll come over here and write it how it's going to be, okay? So I'm going to factor out that u squared, and that leaves behind 20 plus 9u squared. Okay, so here we go. So now we're going to go ahead and do that evaluate, and the thing we're evaluating, right, is our fundamental theorem of calculus vector version up here. So that S of t that I want, I'm evaluating from 0 to t, this derivative. So now I have the square root, and here's the product, right? So that square root of u squared can come out. So I've got a u, and then left under the square root, I have 20 plus 9u squared du. So, okay, I'd call it a u sub, but I've already used u here. So let's see, if w is 20 plus 9u squared, then dw would be 18u. Okay, I've got the u, I need the 18, so here's an 18 and a 1 over 18 outside to balance. Let's see, so I've got 1/18 integrating. What do I have? W to the 1/2 dw 1 over 18 w to the 3/2 divided by 3/2. 2 pops up. Okay, I know it's getting ugly. We're almost done. We're going to work our way back through all of the different letters that we have. Let's see, the 2 and the 18. So now I've got 1 over 27. I have w, but w is 20 plus 9u squared. So 20 plus 9u squared to the 3/2. Okay, so I've done all of my antiderivative, right? So that was the 3/2 part. So now I'm ready to evaluate between 0 and t. Okay. So I've got that 1/27 that's going to hang out all the way in front. And I'm going to have 20 plus 9t squared to the 3/2 minus, so the 0, I do have to actually plug the 0 in here. That'll just wipe out this term here, but I'll get minus a 20 to the 3/2. And this is our arc length function, right? S of t. So at any time t, right, anytime you're along the path that's described by this r up here, right, that we very first started with, t squared, comma 2t squared, comma 3, or t cubed, right? At any point t that we're traveling along that path, this function down here in the light blue box will tell us, right, how far we've gone. Sweet. Okay, let's do one more example of those. Move my camera, and here we go. Okay, so, gosh, that took up a lot of space. I'm probably going to start skipping a couple of steps just because of space limitations. So r of u, r prime of u, I'm just going to write down r prime of u as I go. Okay, so here's r prime of u. It's a vector, so I'm going to keep using those vector bars over the top. So I'll get negative sine u, cosine u, and the 3/2 will cancel that 2/3. So I'll just get u to the 1/2. So then s of t equals the integral. 0's in the domain, so I'll go ahead and use 0 to t square root. Okay, right? So now we're going to square them, add them, root them, right? That's our length of r prime of u. So negative sine squared u is, sorry, negative sine of u quantity squared is sine squared u plus cosine squared u plus, so u to the 1/2 squared, that's just plus u du. 0 to t. Okay, so Pythagorean identity, there's 1 plus u du. So it's kind of like a u sub, but the coefficient of u is 1, so I just do it. So this is to the 1/2, so I'll add 1. I'm writing my antiderivative, FYI. You could do the w thing if you wanted, but you can see that, right, it's going to be the same. So I'm going to get, here's my antiderivative, 1 plus u to the 3/2 divided by 3/2 between 0 and t equals, so 2/3 out in front, and then I'll get 1 plus t to the 3/2 minus, plugging in the 0, I still get that minus 1. Okay, because the whole 2/3 was out in front. So here is the function that describes the arc length. Okay, I want to do one more thing before I leave this topic, and this is called the arc length parameterization. And this is getting us set up for something that happens next when we want to talk about curvature. So curvature, right, is how much is your curve curving? Okay, and for that, we're going to need this arc length parameterization. So this is just a special parameterization of R such that the length of R is always 1, right? Doesn't matter what the variable is inside here or where you're evaluating it, the speed is always 1. So sometimes this will be called the unit speed. Okay? So here's how we're going to do it. We are going to go through and find our arc length function, S of t. Okay, so that's telling us how long the path is. But then we're going to solve for t in that arc length function. We're going to get t in terms of s. So that means we're going to get t equals some function of s. Okay? And then we're going to reparametrize r in terms of s. So it'll be r of t, but this t, we're going to use the g of s function. Okay? All right. Here we go. So the r that I'm looking at, and by the way, right, there are very few vector functions that are going to be like that it's going to be possible for us to find the arc length function. It's just right, things have to work out just so that we know the antiderivative. So you're going to see kind of the same ones showing up again and again. Okay. So, and again, okay, this is the exact same one we just did, but that's okay. We can do it. So here is our vector r, cosine t, sine t, 2/3, t to the 3/2, and we're going to find the arc length parameterization. Okay, so I am going to totally cheat because we did just do that. So our arc length function we have from the page before. So our arc length function, S of t, is equal to 2/3. Hold on, I've got it here, but I'm having a hard time copying it from side to side. So our arc length function S is equal to 2/3. And then I have 1 plus t to the 3/2 minus 1. Okay. And there's my r. How am I going to solve for t here? The answer is very, very carefully. So we're just like undoing. If you're wondering, gosh, this feels a whole lot like inverse functions. Indeed, it is. This is exactly what we're doing. We're finding the inverse, right, of that arc length function. So I'm going to start writing that just as an S. So, and then peeling things off. So, right, start from the outside and peel things off. So first thing that I'm getting rid of is the 2/3. So I'll do that by multiplying both sides by 3/2. So I'm going to have 3/2 S equals 1 plus t to the 3/2 minus 1. 1's the next thing on the outside, so add 1 to both sides. So 3/2 S plus 1 equals 1 plus t to the 3/2. Right, we're looking to get at t. Now it's being held prisoner by this exponent, so raise both sides to the 2/3, right, to the reciprocal. So 3/2 S plus 1 to the 2/3 equals 1 plus t. I know my t's keep morphing their form. Just as long as they're not a plus sign or, right, a plus sign, I guess. And then finally, subtract 1. So the t that I have is equal to 3/2 S plus 1 to the 2/3 minus 1. Okay, so now I'm going to take this and reevaluate my original function r, my original vector function. Now it's in terms of s, and that is, oh my gosh, it is so ugly. In fact, it's not going to fit there. Hold on, we're going to put it down here. So r of s equals the cosine of 3/2 S plus 1 to the 2/3 minus 1. Sine, same thing. 3/2 S plus 1 to the 2/3 minus 1. And then last one is 2/3 times t, so 2/3. T, remember, now being played by 3/2 S plus 1 to the 2/3. Make sure I've got my parentheses in the right spots. Minus 1. And then close off your vector. Oh my gosh. Okay, so now, if you are a glutton for punishment, what you're going to do is you are going to find the length of r prime, right? So you would find r prime of s. So you take the derivative, and then, right, so that's going to be some vector. Then you would find its length, right? So and because of how we've parameterized that, all of your s's are going to add away. I'm seeing a whole lot of Pythagorean identities in there, and this will equal 1 regardless of what s is. So that is what an arc length parameterization is.